Okay, so let's get started. So today I want to discuss chapter 8, the bugging, random forest, and boosting. So these are basically the add-ons on existing methods. So we have studied 3 methods, but that itself isn't really as good as other regression models. So we need some improvement. And these methods, especially the bugging and boosting, can be applied for other statistical methods, such as linear and logistic regressions. Then after that, I do the lab session. And also I uploaded some exercises, but probably we don't have enough time to cover exercises today. So if we have time, then we do that. But we do theory first, then lab session, then exercises. And the final project plan, it's due tomorrow. I think that I wrote somewhere on March 31st but the original syllabus and most notices that says that they're April 1st. So it's due April 1st. So tomorrow at 11:59 p.m. And this time you can use any data set. If data set comes from competition websites such as Kaggle, Crowd Analytics, or others, then your objective should be different from the original objective of the data competition. But other than that, you can use any data. So start 50-30, I deduct some point if you use the ready-made data set, but now that we don't use, I don't impose that deduction because the getting more comprehensive data is more difficult. So 50-30, the more smaller data. But the 58-20, probably you want to get larger, more complicated data. So that's the reason for the difference for data policy. Of course, still, if you use more original data or data from the first source, then you will get some credits probably. When I evaluate I choose which are the outstanding presentations. I certainly highly evaluate it. But you don't have to choose original data set. And I share the screen. Oh, do you have any questions on final projects? Also, I got the question about how many methods do I have to apply for the final projects. We have studied several methods for classification. There may be logistic regression, KNN, linear discriminant analysis, quadratic, and we are studying the tree-based method, random forests, boosting, support vector machine neural network. Maybe we need the interactions, and so on. And my recommendation is at least compare 2 methods. So just doing one method and comparing the 2 different methods are different. But you don't really have to do all the things. Of course, if you compare with many models, that's good, but it's not necessary to use all the models. Okay, so last time we studied tree-based methods. And here are advantages and disadvantages. And you can see that the tree-based method is not stable compared to other methods. And one reason is here at the bottom. So just consider the data set without, with all observations without this observation number 2. Then you can see that the threshold chosen by the tree-based method is this one. The left of this one, actually we have 5 observations with the value 0. I would say this is the binary data, so just 1, 0. And 5 observations with value 0, and 6 on the left of the the threshold, and on the right we have 6 observations marked as 1 and 4 observations marked as 0. So this is, the 5/0, and this side maybe 6/10, and this is optimal threshold. But if we don't have this first observation, but we have the second observation, the threshold becomes this 2. So it's pretty unstable, totally different place. So we wanna make the model smoother and the more robust against this kind of small change in the data set. So methods to improve trees. So it is known that the tree-based methods have a high variance. So seen in the previous page. So you can imagine that the split is largely determined by chance, so it's unstable. The following methods improve the performance of tree-based methods. So one is the bugging. The idea is randomize the training set to make a tree and repeat the procedure and take the average. So if we change the data a little bit and we get totally different trees, then average of those is probably closer to the truth. Especially the tree-based methods, if we have the one split, 2 nodes, we only have 2 possible values, right? If we use the constant function for each part. But if we use the 2 trees and take average, then we have 3 possible values. Or if we have multi-dimensional predictors, then maybe 4 possible values, and that is basically smoother, the decision, surface, and it should perform a little better. And the next one, random forest. This is a special case of bugging. So similar to bugging, but each randomized sample involves a fewer predictors. So suppose we have predictors x1 to x10, and usually we choose just the best one to split it into 2, and for example x1 first. Then next, maybe we divide the one part of the region into 2 parts by another variable like x6 or something. But the random forest allow only a couple of variables, for example x1 and x7 and x10 to make a tree. So if we have the tree of size 10, then we have 9 splits. So all 9 splits should come from either x1, x7, or x10. So in that way, the trees are different each other. So the bugging is taking average of 100 trees, for example. But if we make tree based on different set of variables, then the resulting trees are different. So if we take average, a kind of diversity matters. So if we average out diverse trees, then the final outcome is better. So it's counterintuitive, and I'm not exactly sure how people come up with the idea, but actually if we limit the number of predictors for each tree, the performance gets better, empirically. The boosting is slightly different idea. Somewhat similar to bugging, but different. So gradually determine the tree. So, we have, for example, y is equal to, okay, so suppose the y bar is 0, just for simplicity. And we fit the model, y is equal to ax. And the estimated a may be 5. But we only choose maybe, okay, so then y hat is the 5x, right? But we only reflect part of it. For example, the 0.01 y hat. So that is 0.05x. Then we consider residual y minus 0.05x. We say this as y2. Then we regress y2 on I mean, we apply the tree-based method on Y2, then we go on. So basically, similar to, taking average of 100 trees, but each time that we update the Y value, we consider just the residual of this tree-based method. So the result is different from bugging. So yeah, it depends on the case, which method is better, but often the boosting, the performance, outperforms the bugging. Yeah, so we start with bugging. Do you have any questions so far? So these methods can be applied for other methods. For example, boosting can be applied for linear regression or logistic regression also. Logistic regression is a little bit harder, that we need some trick, but the linear regression, certainly we can do that. The bugging is slightly different, right? So still maybe we can do that, but probably if we apply to the linear regression, probably the result doesn't improve because linear regression is originally pretty stable. Yeah, but anyway, so these methods can be applied to other statistical models. Bugging, so suppose that the training set has n observations, then we repeat the tree-based methods b times, capital B, maybe 100. And the steps are, at first, the bootstrap n observations with replacement from the training set. So original data set may have, suppose, 500 observations. Then we bootstrap 500 observations from the original data set with replacement. So some observation can be chosen twice or 3 times. Some observations are not chosen. Then fit the regression and let f hat sub b of x be the fitted function. Then we take the average. So that is the bugging. And how to determine b? Yeah, so theoretically, all hyperparameters should be chosen by cross-validation or similar methods. Yeah, so yeah, that's right. But the B is, not as important as, the coefficients in the model. So it's a hyperparameter. Any questions? And also that we have some other hyperparameters, such as the maximum number of nodes for each tree. So since we average out the multiple trees, often we restrict the size of tree, max number of nodes, maybe size, size of the tree. And that should be also optimized. Sometimes we limit this, then performance gets better because, again, the trees, different trees have different, shape. If we allow everything, every time trees are similar. Of course, we have some randomization by observations, but sometimes it's too similar. And the minimum size of terminal node also, it can be controlled. Yeah, so illustration of the algorithm. So just to think about a similar situation, the simple situation, we only have variable x, one variable as predictor, and the y is continuous scale response variable. Then suppose that we have maybe 6 observations, such as this, almost linearly distributed. And what's the result of tree-based methods? Okay, so just in case I copy this, maybe it's a little bit too large, maybe. I want to put 3 graphs. Okay, so suppose that we observe this data set, and then what's the optimal tree? Probably we have 6 observations. So the first one is the average of first 3 observations, and okay, so threshold is here. Then second one is the average of the last 3 observations. So this is the one tree. So I would say the f hat 1 over x. And next, okay, so we bootstrap, so we have different observations. For example, maybe we don't have this one, but we have maybe this observation twice. Okay, I put here. So in this case, I don't know. I think probably this is a little bit too close to the center. So well, maybe we choose this observation twice, this observation twice. Then I don't know the optimal tree, but it might be different. So the threshold may be here, and the 3 observation average of here. So maybe average of here, so maybe around here, and average of these 3 observations here. And the last one, maybe that we don't have this observation, but we have this observation twice. So in this case, the maybe, I don't know, but the threshold comes here. I would say this is A, B, C, and the threshold is here, and the here is the fitted curve, and maybe here is the fitted curve. So if we average out these 3, this is f2 hat and this is f3 hat of x, then maybe this is, maybe I should copy this once more, but so probably the resulting curve is smoother. I mean, the step function with 4 levels. So I'm not exactly sure about for this specific situation, but here is maybe B, and here is maybe C, and the resulting fitted values are probably around here and like here and here and here. I don't know, like this. So the decision boundary is smoother in the sense that we have more steps. So certainly it's better than, you know, single one, this one, this one, or this one. So most points that we can capture the closest point, closest level. So it's smoother boundary, and we don't use any more parameters or something. So just we apply the same method multiple times with randomized data set. So we are not using more parameters. We are not constructing a more complicated model, but just averaged out several experiments. Then boundary that should be better. So this is the idea of bagging. Yeah, so machine learning methods, often we just see the methods and the statistical package, and the package is a black box, and we put just the data and we see the final performance, such as root mean square error. But sometimes it's useful to see this kind of idea on the method. Do you have any questions? So in real examples, we have multiple predictors, so the situation is more complicated. But the idea is, that we average out, then we have a kind of smoother curve, kind of the step function. Yeah. And so here, the out-of-back error estimation. So this is a kind of the simplified version of cross-validation. So cross-validation, we apply methods with training set, then we evaluate the error by the test set, right? So basically we separate the original data set into several equal pieces, and we reserve one for the test and the others as training, and we repeat. We repeat the procedure to calculate the error size. And out-of-back error estimation is incorporated with this bagging procedure. So in bagging, we random sample observations from the original data set. So we choose several observations, and typically, if we choose n observations out of n with replacement, about 2/3 of observations are chosen. And the other 1/3 will be used as the test set. That is the out-of-back error estimation. Since anyway, during the computation of the bagging, that we separate the data set, so that we just exploit that to evaluate a kind of similar thing to out-of-sample error. The test error. So we kind of recycle the sampling results. So it's more, time efficient. So in each tree created in bagging, unused observations are called out-of-back observations. So this is an example. Suppose we have 6 observations, and so this is the training set, and the bootstrapped sample is the 513235. Then 4th and 6th observations are not used. So this is the out-of-back observations. So we use the tree. So we apply the tree-based method for these 6 observations. Then we evaluate the error with the remaining observations. So that is the method for out-of-back error estimation. So we use the OOB observations as the test set to evaluate the error size. And the mean of OOB error size is the OOB error size. And OOB error size is the good measure of test performance because it's similar to cross-validation. Yeah, so this is one interesting graph. We haven't explained random forest, but just focus on the bagging. So this is OOB error estimation for bagging method. You can see here. And this is actually for the training set. And if we use a new test set to evaluate the error size, then that is this black one. So actually the out-of-back error estimation underestimates the test error. Yeah, I think this is a little bit strange. The both are basically, the test error, right? So that we don't use the training set of the training set information to evaluate test error. So that should be the same, but actually the test error is larger. I don't know why this happens, but practically this happens often. So even if we use OOB error estimation test set, that we have larger error. I don't know, this comes from some optimization of hyperparameters, maybe. And sometimes it comes from the slight difference in the characteristics of the training set and the test set. I don't know exactly why this happens often, but just the note that the OOB error estimation sometimes underestimates the true error. Do you have any questions? Yeah, this comes from the textbook, so I'm not. Yeah, so maybe we have to see the exact specification. Yeah, this is from the heart data, and yeah, so it does not mention how to divide the test and the training data. Yeah, so I don't know exactly where this difference in error size comes from. Yeah, maybe the out-of-bagging, still some information is reflected in the hyperparameters that makes out-of-back error estimation smaller. Yeah. Yeah, just note that OOB error estimation underestimates the error sometimes. Okay, so the next one, the variable importance measures. So yeah, importance of each predictor in bagging is represented by how much the variable decreases an error measure, such as the sum of squared error for regression. And this graph is standardized, so that the most important predictor has the variable importance of 100. Standardized, so that this is 100. So in this data set, the THAL variable is the most important to predict the response variable. And the next important variable, the CA, is maybe 55%. So the importance level is 55% compared to the THAL to decrease the sum of squared errors. And others also. So if you have many predictors, then probably you have to cut off at some points. Yeah, but this is a kind of similar to the the table, the summary result of linear regression. So linear regression, we see significance, the t-value, and so on. Also, we can see the coefficients, so how much it affects the response, we can see. But for this kind of complicated methods that we cannot really see how much impact variables has. So we see this kind of just numeric measures to see which variables are important. If we don't have this, the procedure is totally a black box. We don't see which variables are more important than the others. So this is a machine learning method, so that we don't have any significance. For example, we don't know how much how important this is. Just random results can reduce the sum of squared residuals to some extent. So maybe this is statistically not significant, but we can just see numerical results to see which variables are relatively more important. And do you have any questions? Okay, so the next one is random forest. Random forests are the same as bagging, except for the number of predictors allowed for each tree. So the number of predictors allowed for each tree is smaller in random forests. So suppose we have p predictors, then random forests often allow the only one third of p. So if we have 10 predictors, we allow 3 or 4 predictors. Or sometimes m is equal to square root of p is used. If we have 10 predictors, maybe about 3 predictors. Yeah, so m is equal to p, then random forests are bagging. So the idea behind random forests is to diversify the generated trees. Yeah, so the p is smaller, so estimation is easy. The m is smaller, so estimation is easier. And it has less information, but magically it performs better often. So this is bagging. M is equal to p. And m is equal to p over 2. And m is equal to square root of p. So these are random forests. And you can see that actually the blue one and the yellow one are similar, but the green one consistently performs better than the other methods. So this is test error size for some classification problem. So often the random forests performs better. So m is a kind of hyperparameter, so it should be maximized by cross validation. Should be chosen by cross validation. But often m is equal to square root of p or p over 3 that performs better than the bagging. Yeah, maybe that we go back to the original one, and you can see that in this case the random forests performs better in not this one. Random forests performs worse than bagging for OOB error. But if we actually evaluate the test error, the random forests performs better. So OOB actually worse. But if we use the test error, this is basically the target. So actually it's better. So random forests performs better than bagging. So of course it depends on the case, depends on the data. Any questions? And the next one is boosting. So boosting is a method to fit the statistical model slowly. So that is, the fitted values are changed by small amounts at a time, but the model is fitted many times to obtain final predicted values. So boosting is a general approach that can be applied to many statistical learning methods for regression and classification. And algorithm is here. So R is residual. So we update the predictor. So at first, suppose that all fitted values are 0 and the residual is equal to yi. So generally, yi is the yi hat plus residual. So if yi hat is f hat of x. If this is 0, then of course the yi is equal to ri. And just first we start with the original yi. Then we repeat the procedure many times. Capital B is a large number, such as 100. And fit a tree model with D splits. D is another hyperparameter. It's a fixed number to the training data. Then we get the fitted value. Then, okay, so originally f hat is 0. Then we add the lambda times f hat sub b to get the new f hat. So lambda is typically a small number, for example, 0.01. So lambda and b are related hyperparameters. So it's natural that, for example, B is 100 and lambda is 0.01. So we reflect only 1% of the obtained results, but we do it 100 times, then maybe it's similar to usual regression. But yeah, not necessarily B lambda is equal to 1, but the B and lambda are closely related. Larger B, I mean, smaller lambda requires larger B usually. And then, okay, update the residual. So new, maybe I would say the new Ri is the old Ri minus the lambda times the B F hat sub B. So we update the residual. Then we repeat this procedure. So in bugging, we simply fit the model 100 times, but the boosting, we update the, so update the, response variable each time. Bugging, the response variable is Y, but the boosting, the response is Y initially, but after that we, update that into R. So that is, the reasonable. That sounds very natural and reasonable, because suppose that we use the X1 to explain Y, then we reflect a part of it into Y. But if that is enough, we use enough information from X1 to explain Y, then after that, maybe a different variable is chosen. So that sounds pretty natural, the method, right? So we reflect the information of Y, X1 in the model. Then if we reflected enough information from X1, then maybe we choose another variable, another predictor to explain the remaining part of Y. Yeah. Right. So I think that I mean, several years ago, the Zillow, do you know that Zillow is a real estate company? The online real estate information company. So Zillow launched the data competition to explain the house price by other variables, such as the zip code and the size of the house and so on. But I think at that time, the response is the residual when the Zillow, the company Zillow, they fit the model. So basically, the Zillow fits the model, but maybe they can improve more. So they posted residual and other information to explain more. So probably it's obvious that, for example, the size of the house or the number of bathrooms matter for the house price. So just they excluded those factors, then the remaining part they want to, they want the attendees to, explain. Yeah, so that's it. And you can also say that the f hat x is the summation of lambda times the f hat b, because this is the updating function. But the difference from bugging and boosting is that in boosting, each f hat is calculated based on the residual, not the yi itself. So every time response variable is updated. And there are hyperparameters. The b number of trees is the hyperparameter, and shrinkage parameter lambda is also a hyperparameter. Typically b is a large number, lambda is small number, such as 0.01 or 0.001, and small alpha often implies a large b. And the number of splits in each tree, usually it's small, d is equal to 1. So we don't really need a large d, right? So because suppose we have x1 to x10, anyway, that we repeat the procedure many times. If x1 is most important, we apply, we use the information of x1 to explain y. But after several steps, then it's enough so that another variable comes in. So we don't really need the two variables at the same time. So often the d is equal to 1. But theoretically, we can choose any value of d. Any questions? So boosting the image is similar to the previous one. So maybe we use the similar graph as before. So suppose that we have 6 observations, 1, 2, 3, 5, maybe 4, 5, 6. Oh. Yep. And we have some threshold. Suppose this is optimal threshold. Then, okay, so estimated tree is here. Maybe I use the dotted line. So this is the just based on usual tree. If we use usual tree, this. And suppose that the data is normalized so that the average is 0, then okay, so even if the fitted tree is here, only a part of observations is reflected. So suppose that the lambda is equal to, for example, 0.1, and only 1/10 of the information is reflected. So maybe obtained tree is here. Then next steps, this is step 1, and step 2, that we use the residuals. So residuals are almost with the same graph as the original graph, but the residuals are here. So slightly smaller than original observations. So suppose this is 0, then maybe slightly closer to the line. We cannot almost see, but that's the slightly closer. So then, okay, so in this case, only one variable x, so we use the same variable. So we use the same variable here. Then again, the average is around here. Average around here. But we reflect only the 1/5 of the 1/10 of the value. So like this. I think that we need multiple variables to make it meaningful, but each time that we choose just a small function. So this is f1 hat. This is f2 hat. So we take average of this to make it a more complicated curve. So sometimes if we choose a different variable, maybe I would say that this is x1 and this is x2. So once you reflect the 1/10 of the observation from x1, then maybe x2 is more important than x1. Then we take this. This is f2. So f1 hat is a function of x1, constant with respect to x2. f2 is a function of x2, but is constant with respect to x1. So if we take average, we make a more complicated function of x1 and x2. So in this case, in this way, the boosting will get the fitted value. And this is one simulation on the same data set. And the boosting and the random forests, the performance, the random forests have, actually the boosting has smaller the test classification error than random forests. And actually the boosting, boosting with depth equal to 1 is better than depth equal to 2. So it's similar to the situation between random forests and the bugging. So random forest limits the number of variables used each time, and then performance gets better. But here, boosting also, better. If we choose smaller number of variables at a time, then actually the fit is better. Yeah. Yeah, so often the boosting performs better than the random forests. Yeah, so the bottom line is that the tree-based method is a good idea, but to have the practically useful the performance that we have to use, there is a random forest or boosting. And data competition. In data competition, the more advanced method, I think it's called the XGBoost, is more popular. I think it has, I forgot the details, but it adds more ideas on this tree-based methods. Any questions? Have you ever used boosting before, especially for engineering major students? No. Probably math students, maybe. I haven't ever heard of it when I was a student many years ago. So you can see that this kind of methods has less interpretation compared to regression because we don't have statistical significance, more prediction performance-based methods. So some theorists, like economists, they don't like it, probably. Yeah, so now that we discuss the 8.1, 8.2, 8.3 in R, and the tree-based methods, probably you don't use it many times because anyway, we need the random forests or boosting to get meaningful performance. Tree-based methods, we use the tree package, and we use the ISLR package for the data car seats. So car seats data have 400 observations with the 11 variables, and basically this is the data for the car seat sales. I think the booster seat, the child seats sales in different stores, 400 different stores. So 400 observations are stores. And this is the sales. So this is regarded as response usually. And these are predictors. The probably most important factor is price. This is for the same product in 400 different stores. And lower the price, then sales is higher. But also the comp price, the competitor's price is important. So this comparable price, they may have some information. Income is the income level where the store is located. And this is advertising amount in the market. I don't know how 400 stores are chosen, but they may be in different regions. So we can even see some advertisement amounts in TV newspapers and so on. And population also matters for the sales. That's understandable. And the shelf location. So where the shelf is located. If it's just the in front of the entrance, then probably sales is higher. If it's in the corner of the store, then sales is lower. So that is also regarded as important variable. And age matters. If every people living there are 60 years or older, then the smaller number of children, so cells should be lower. Educational level, maybe higher educational level, more cells. We are not really sure. Urban or suburban, maybe urban, maybe a smaller number of people have cars. US or not US, yeah, it may matter. US, yeah, I don't know. Yeah, so the data looks like this. So usually there are two, convenient way to see the data. One is structure and the other is head. And we do two analyses. The one is just the cells as predictor, and the other is the dichotomized cells as predictor. So here, dichotomized version. So cells is more than 8 or less than 8. Maybe if less than 8, the economically, selling this item in the store, that does not make sense, for example. So now that we start with this, the dichotomized one, so binary variable. So we predict whether sales is more than 8 or less than 8. I don't know, this is maybe 8 per day or something like that. And yeah, we make it as factor variable. Then data frame, we add this variable to the data frame and we name it as D. And the response variable, and the predictor variable, of course, we cannot use cells, so we discard discard D. Then we remove high because high is already included in the data. So just to avoid confusion, that we delete it. And we apply tree-based methods. The format is similar to the linear model. So response variable. And this is predictor variable and the data set. So dot means the all variables except for this high. And summary of tree, that we get this. I think this isn't really meaningful, but this is basically the likelihood. And this is the error rate. And this is the terminal nodes. So that we make a bigger tree at first, then after that we trim it, we prune it. So 27 is the largest tree. Then we put plot. The plot makes this graph. Then after that, we put the description. So location is bad or medium. So medium. Then here, and the location is good here. Medium. And we split, and then so the description is given by this text. So pretty is equal to 0. I think there's some formatting problem. So if we don't put this, then the result doesn't look nice. And CX 0.7, this is the point size. So if you want to make these letters larger, then you can make the CEX value larger. And and based on this decision rule, how many are predicted correctly? So we can get this by this. So predict function. So after this, after separating cases for each node, we can predict whether the probability of yes is 0.5 or larger or smaller. So then we can make a table. So this is the truth, actual result. And this is the predicted. So if truth is true, then out of 164, 151 are predicted correctly. So this is sensitivity. If the truth is no, actually out of 236, 213 is correct. So 213 over 236 is specificity. Or you can calculate the error rate. Error rate is equal to 23 plus 13 over, 23 plus 13 over the sum of this. So 23 plus 13, 213 plus 151. So probably this is, okay, so 36. So 36 is equal to over 400, so 0.09. I think this corresponds to this error rate. Yeah. But this is the overly overfit, because that we use all observations, then we see just the how many observations are the categorized correctly. So the more fair way to estimate the test error size is doing validation approach or cross validation. So training set and the test set, we use 200 observations as training, the others as test. So DTRN is training data, DTST is the test data. And we use training data to fit the tree. And if we use those samples, then we get similar results. Actually, here 200 to 20 over 200. But if we think about the test results, that may be different. So at first, we use training data and use cross-validation to optimize the tree size. Okay. So if we use just training set to evaluate the performance, then more complicated tree always is better, but we overfit the model. So we do cross-validation, then we see what is the optimal size of the model. And this is size of tree size. So tree size is 1 to 28, right? So the largest tree is 28, but the 27 maybe 27. But based on the the size of penalty, this is the size of penalty. Size of penalty is in our slides denoted as alpha. And this case slightly different to alpha because we have like negative infinity or 0. So I think the K is the logarithm scale. I'm not exactly sure what this means, but probably e to the power e to the power K or something like that. So K is larger, more penalty, so tree is smaller. K is small, the less penalty, so size is larger. K is negative infinity, probably alpha is equal to 0, so we choose the largest tree. But it's not really 27, so probably 27, 18 to 27, that we have the same performance. That is the case. And this is deviance. Deviance is usually the sum of the squared error for a linear case, but this is quadratic. So this is binary case. So usually the deviance, the likelihood function, but we specified the misclassification. So this is the misclassified. Classified observations. Number of misclassified observations out of 200 training observations. And actually the minimum is 40. So, the 40 over 200 is equal to 0.2. So much larger than 0.09 obtained in the previous result. Because, this is, cross-validated the result. So That's why it's larger. So basically, optimal k value, the hyperparameter value, is corresponding to this. So fifth or sixth one from the right. So 1, 2, 3, 4, 5, 6. So these ones are optimal. In terms of tree size, 5 or 6 is optimal. Yeah, so this is the case. So tree size and the deviance. So misclassified error by cross-validation. So 5 is optimal. Maybe 6 is also fine. So we choose this. This is the the correspondence between k and the deviance. So here, maybe around here is the best. And this is classification rule. So originally we have 58% of no and 40% of yes, I think. And at first we divide the case by price. If price is less than 92.5, then we have more yes. So 87.5% yes. And the price is more than that, actually the 0.666. So the 2/3 of no. So sales is less than 8. So sales is more than 8 with 87.5% probability, and no with 67% probability. So probably our decision that should be made is we reduce the price to 92.5 or something like that, maybe. And after analyze this, even if price is higher, shelf location is good, then maybe it's good. So shelf location is bad or medium, the result is even worse, but the shelf location is good, then still the sales is higher. So if they have, store agrees to put the item in a good place, still it's worthwhile. So maybe we can boost the price if the location is good. And so on. The next criterion is this. Yeah, and this is the resulting. So we use the best. This is the tree size. So we got the result. And we have several different ways to prune the tree. And also we want to make the table to see how many are classified correctly. So yeah, so predict function we use, and the model, and this is the test error. So this is test error. And type is classification. So then table. Then you can see that this is, I think that this is predicted value. Okay, so predicted is first. So this is the truth, actual. So these are correct decision and these are incorrect decision. So for example, if actually sales is larger than 8, out of 80 observations, the 46 are predicted as, sales is more than 8. And this 100 out of 120 stores less than sales, with sales less than 8, we have actually the 100 is predicted as no. So this sounds pretty good. And 54 over 200 is the error rate, so 27%. It's even higher than the training set. I don't know why this is almost always higher than this cross-validated one. I think probably some hyperparameter problem. Hyperparameters reflect some training information so that the results looks too good. So fair estimation of the out of sample error is, test error is 27%. Yeah, do you have any questions? Okay, so the next one is the regression tree. So this is the typo, so regression tree. So almost the same, only the difference is the response variable is continuous. So just we use these cells. So this is the original figure. So you can see that the price is higher, the sales is lower, negative relationship. And also advertising more than sales is higher. So we have positive relationship. And income maybe slightly positive. This is also the comparable, the items price is higher, probably it's positive. Population, not sure. Maybe too many observations to see. I think that in statistics, always we have optimal number of observations, which makes the plots more readable. Time series data, usually 5 to 10 years, it's better to see. If we have 100 years of data, monthly data, we cannot really see the seasonality and other characteristics. So here, maybe observation, too many observations compared to the size of the plot. And also sales to other variables and shelf location. It's really hard to see because the many observations are at the same point, but the shelf location, actually this too is better than others. I don't know, the two means what, you have to see the data set itself. Age, you can see the higher age, maybe sales is lower. I think too many observations here, so we are not sure what this means. You can also use the correlation plot. You can calculate the correlation. So this calculates the correlation matrix of these variables. If we have, how many variables here? Sales and the 5 and 5, so 11 variables. So this is 11 times 11 matrix of correlation. And if you use correlation plot, then you can get this kind of plot. And you can see that to explain sales, the price and the shelf location, possibly age, possibly advertisement. So these are important. Maybe less important variables are education or urban or population and so on. Maybe population does not matter because the number of stores depends on the population. So actually that is canceled maybe. And if you want to see the numbers, then you can put the number option in correlation plot, CORR plot function, then you can get these numbers. So this may be useful if we have not too many variables, but suddenly we need more space to see the data. So price, shelf location, age, advertisement have higher correlation than others. Yeah, and then the regression is almost the same. So we prepare the training and the test set, and this is just the same. Okay, so this is just the same. So the tree method automatically determines what is the response variable. So here response is continuous. If factor variable, that they fit just the classification problem, then regression problem, then R automatically do it if response variable is continuous. And still, we have the same graph. Only the difference is the answer is numeric. If shelf location is bad and but the price is lower than 19.2, then still the sales is 8.32. Shelf location is good, probably this is good. And the price is less than 109.5 and age is less than 44.5, then it's optimal maybe most ideal case, and the sales is 14.01 on average. So last time this is yes or no, but here numeric, so average value, estimated value. And the same thing for the optimized results. So here the deviance is the residual sum of square. So it's not the misclassified observations. So the criterion is different, but the other things are the same. So K value and the size and so on. And this is actual training and predicted in the training set. So the predicted value and actual value. Yeah, so you know that the tree. So this is the we have 5 nodes, right? So the tree size is 9. So we only have 9 possible. So tree size is 9. So 9 possible the response value. Fitted value. So we see only 9 levels. So 1, 2, 3, 4, 5, 6, 7, 8, maybe 9 here. So 9 levels. And actual sales is continuous, 0 to like 16, but the predicted value is 9. But the overall, the predicted value explains actual value. And here is the error size, the mean square error for training set. Training, right? And if we use the new dataset test set, then we can calculate the test performance. And the test, we have the smaller correlation. Because we use the model with the training set. And this is test error. Test error is 5.18. So training error was 2.56, so it gets worse. Yeah, so that's the way on how to fit the tree-based methods. And it looks fancy, but if we compare with linear model, what happens? So this is linear model, usual linear model, linear regression model. Then, okay, so at least we do stepwise regression to be fair. Then these variables remains, the comp price, income, advertisement, price, shelf location, and age, and these are all significant, even though we only have 400 observations. Then this is training error, and this is test error, and it's much better. So test error was 5.19 before, 5.18. So this is much smaller, so much better. So usual tree-based method is not as good as regression model, because we only have the 9 dichotomization, so 8 dichotomization. So linear model, we see, more, numeric relationship between X variables and Y, so it performs better. And the next time that we see how much bugging and random forest improve the performance. Okay, so do you have any questions? Okay, so next time that we do the remaining thing and do some exercise. Okay. Yeah, okay, so if you don't have any questions, we'll see you next Tuesday. And the final project plan is due on tomorrow, April 1st.
Okay, thank you, Professor. Have a good night.
You too.